Hi, everyone. Thank you so much for sticking around for this presentation. Um, my name is Julia. I work at Neon EVM as a developer relations manager. And today I want to talk about going beyond the EVM and triggering external logic from your Solidity contracts. And in particular, we are going to be talking about how to trigger Solana programs from EVM projects. My name is Julia Gallen again. I entered the industry in 2018, and I work in various EVM projects, from wallets to infra to even prediction markets. But I do have a very different background. I come from computational linguistics originally, and at the moment I work at Neon EVM to help EVM developers bridge this gap between EVM and Solana and expand their user base to Solana users and also to Solana liquidity. So usually expanding to Solana from EVM is a very painful project because obviously you will need to maintain two code bases, you will need to learn Rust and create your project in Rust to interact with Solana programs, or another way would be to use a bridge, but this will add an overhead. And Neon EVM brings the two worlds together in the best way possible because for EVM developers, it means that there is no painful learning of Solana architecture or no need to learn Rust. They can stay within their comfort zones of Solidity and EVM infrastructure, all the familiar tooling. They can use Hardhat, Foundry, they can use Remix, and they can connect to Ethereum RPCs as they usually do. And at the same time, they can add the good things that Solana has, which is the parallel execution, which is lower gas fees, and obviously a new user base and new liquidity pools. How does Neon EVM do that? Well, it has two main components which allow for this function to happen. And these components are the Neon proxy, over there, and the Neon EVM program. And the end a goal for an app here is to be able to connect the users with both EVM and Solana wallets and interact with Solana programs and SPL tokens, so tokens on Solana. And for both, Neon EVM makes a native experience, which means that they don't have to use a bridge or anything like that. And EVM wallets are just connected to a dApp frontend. They send a typical EVM transaction, which is picked up by Neon proxy, which is just a typical Ethereum RPC. And Neon proxy translates this EVM bytecode, EVM transaction, into a Solana-style transaction. We are going to see later how exactly this wrapping happens. And it sends it to the Neon EVM program, which is deployed on Solana and contains precompiled contracts that execute this double hybrid transaction natively directly on Solana. And thus, the EVM wallet can connect to SPL tokens and to Solana programs, such as all kinds of Solana dexes, Jupiter, Radium, Orca, etc. And at the same time, Neon EVM allows to use Solana wallets to connect to all these kinds of Solana programs. But you would say, why would you need an Neon EVM for that? Because you allow your EVM dApp to give Solana native experience to people who have Solana wallets. So basically, they connect to your EVM dApp with a Solana wallet and send Solana transaction, which contains the EVM bytecode to Neon EVM program that also executes this directly and natively on Solana. So before I show you how Neon EVM wraps an Ethereum transaction into a Solana transaction, let's briefly compare EVM and Solana transaction objects. And well, as you all know, this is an EVM transaction object, which is very simple, very straightforward. But this is a Solana transaction object, and it is complicated. First of all, it is instruction-based. So you can see that all these operations are packed into instructions, and for each instruction you have to generate a very particular list of accounts. Well, like everything is an account on Solana. I'm not sure how well you're familiar with Solana, but basically Solana treats like tokens as accounts, like everything basically is an account on Solana, and you need to generate very explicitly all these accounts in a very particular order here. So to be able to do that, Neon EVM, sorry, I'm not moving the right direction. So Neon EVM basically wraps this Ethereum-like transaction into the data field of a Solana transaction, and it adds an EVM program address in accounts list into the program index field, and it also generates all the required accounts in the libraries and puts them into the accounts list on Solana. So it kind of both splits the Ethereum transaction and puts that into Solana transaction, but also it generates all the needed accounts and translates the instructions to be able to put them within Solana transaction. And it does it with the help of this composability feature, which consists of libraries and precompiled contracts. So at the moment, composability is available for these programs on Solana, and these are the native programs and a couple of custom programs on Solana, so that you can connect your EVM project to system program, which handles account creation, to SPL token program, which handles everything related to tokens, the associated token program, which handles the creation of associated token accounts, which is like an account on Solana, and Radium DAX and Metaplex for managing metadata. So this is the first part of composability, the precompiled contract, and this is the basic structure of the precompiled contract. This one is called I call Solana, and this one is a major precompile because it handles the execution. So basically it handles the instruction, then it also gives us the pair account with a getter, and it also gives us a Solana address for Neon address, which we need for authentication. And basically the main function here is the execution, because I call Solana precompile is the one you send your function calls to be able to execute them within Solana. And these precompiles, including the I call Solana, can access Solana state, they can create accounts, execute instructions on Solana, and a very cool thing is that they also can batch multiple instructions to be executed within one Neon EVM transactions. For example, all these instructions like create an account, initialize the token mint, create metadata for this account, and mint to an account can be all put together and sent in one transaction. And the second part of composability is the libraries. The composability libraries basically help with creating these instructions with the helper functions, getting data from Solana state with the getter functions, handling errors with the custom errors in one of the libraries that allows to handle reverting the execution on Solana, which is a very painful topic. Then it has Solana constants and also handles Solana rent management and all kinds of calculations. So basically, you need to create a caller contract, which is written in Solidity, and all you need to do to make this composability work is that you need to import the libraries and use them in your function calls, and send the final call to execute to the precompiled contract. So a caller contract, this one is attributed an account owned by Neon EVM program on Solana. It requests a payer account. It owns the accounts that are created on Solana, and also it implements the authentication logic by getting Neon address for Solana. And currently we have 5 libraries. The system program library that allows to create accounts, the SPL token program library that allows to manage tokens, the associated token program that allows to create ATAs, associated token accounts, Metaplex for metadata, and Radium program for interacting with Radium DEX. But you can also actually interact with Jupyter and Orca through the Radium program and through other libraries as well. So there is, like more to it than here in the slides. So this is basically the basic structure of a caller contract. Here we have an example of a transfer function in a caller contract, and it always starts with the authentication, where we get our Neon address using the iCall Solana precompile. Then we also derive the ATA so that our tokens can exist on Solana. We format the instruction using the method from one of the libraries, and we prepare the instruction again using the methods from our libraries, and we send the call to the iCall Solana precompile to execute this instruction. Today I want to have a bit of focus on the Radium program library. So we are going to see how Radium program library allows us to make a swap on Radium DEX from a Solidity contract. And Radium program library, as all the other libraries at Neon, consists of 3 things. So it has helper functions which generate the instructions. It has data library which provides getters so that we can fetch data from Solana state. And we have the errors library, which allows us to handle the errors. And this particular library, Radium CPMM program is actually a analog of Uniswap v2. So the instructions that we can generate are very much in line with what you can do with Uniswap. So you can create a pool, basically with this instruction, create pool instruction, you deploy a CPMM pool on Radium for a token pair. You can add liquidity, withdraw liquidity, lock liquidity, and get an NFT position. You can collect fees when there's been some traffic in the pool, for example, a swap. And you can use the swap input and swap output instructions to either make an exact swap for X amounts of token B or the other way around. And the getters are very much in line with the helper functions that we have. You can get the data from the pool, about the config, the token in reserve, the LP amount that is accessible. You can convert the LP amount to reserve amount and calculate the swap output based on swap input and slippage, as well as do the other way around. Calculate the swap input based on output and slippage and also pool conditions. So the caller contract, this caller contract is very much similar to the one we saw before, but it has more handling of tokens, which is, of course, obvious because we are dealing with a swap, and we need to swap one token for another. And for this, basically, we pass very typical parameters, pool ID, input token, output token, amount that we want to input, and slippage. And we generate the token mints using the ERC24 SPL token, which is a hybrid token created by Neon EVM to make this sort of connection. Basically, it is an ERC wrapper for SPL tokens. So if we need to get a SPL token, we can just derive it from an ERC24 SPL. And basically, this is how we get the input and output token mints. Then we get the Solana pair using the iCall Solana precompile. Then we get the associated token account using the input token mint and the pair account. And this is the associated token account to which we are going to transfer from our Neon EVM address so that we can handle these tokens on Solana. And this is where the transfer happens. So before we can handle the tokens on Solana, we need to move them from our EVM address to a Solana address. And this associated token account is going to handle the tokens later. So we transfer from the PDA. PDA is a program-derived address, which we derive from our message sender. And we move the tokens from this intermediary account to an ATA, associated token account. And later we can work with these tokens on Solana. So this is an auxiliary part. It doesn't exist in all caller contracts, but here we also use it because we optimize for gas fees using the pre-made accounts. But later, as usual, in all caller contracts, we format the swap instruction using one of the methods from our libraries. In this case, it's swap input instruction. And we execute the swap on Solana, calling the iCall Solana precompile. Yes, this is all. And to look at the instruction that handles that within the library, let's see how it does it behind the scenes. And basically, this swap input instruction first looks very much like a call contract because we pass the same parameters. But then we get the pool data, we get the accounts with their flags, which is signer, which is writable. This is the thing that is generated within the swap method here. So basically, this is a swap input instruction, but there is another layer even beyond this, which is a swap method, where all this account creation happens. But at this stage, we are only getting the data. Then we calculate the minimum swap amount output based on slippage and pool condition. And this is also happens in the library. This is not something that you have to do. And the next thing is that the library builds the swap input data, and it converts big endians to little endians because Solana deals with little endians. And this is also a conversion that happens within the library. And the swap method, which is like the bottom layer of everything that happens in the swap, also, well, the beginning looks very similar. So we get the data, we get the accounts, check if we have pre-made accounts. And then the swap method generates all these accounts in the correct order that Solana expects to have in this kind of instruction. And as you can see, there are all kinds of accounts here for the payer, for the tokens, for the pool data, the pool ID. So basically here you can see that like everything is an account. Then the method is assigning the signer flag, and then it assigns the writable flags to the accounts that can be written to. They can be, you can write state to them, or writable are also executable accounts. And basically by the end, you get these two sides of the transaction. You get an EVM side and a Solana side transaction. And this is a screenshot from Block Scout where we have the Neon EVM transaction. And as you can see, it contains two Solana transactions. And if we open the Solana side transaction, well, there are like other instructions here, but also these are the most important ones. You can see how many transfers happen here, the account creation. So first we transfer the tokens from PDA to ATA, then we generate all these accounts, we check the transfers, then we make a swap to another token, and yeah, basically that's it. Yeah, and this is how the swap happens with Neon EVM from Solidity contract to a Radium DEX. And basically, we saw that we used the libraries and precompiled contracts to generate the instructions from our caller contract. And we sent them to the precompile, which executed them on Solana. And as a result, we got the EVM side transaction and a Solana side transaction. Thank you very much for your attention. If you have any questions, I think we still have time. Yes.
Oh, okay. Can I do like interaction atomically between like EVM transaction with the Solana transaction? Let's say I want to swap USDC. I want to sell my ETH to USDC and then use that USDC to buy some token on Solana. Can I do it atomically within one transaction?
Yes, that's exactly what you can do. Yes, you can batch those two transactions into one instruction, well, into one transaction that contains these instructions, and yeah, swap it on a Solana DEX.
But one transaction is happening on EVM and one transaction is happening on Solana. So can it become atomically within, like, let's say one error revert on Solana, can it also trigger reversion on EVM?
As I see it, that would happen. So if you do that through Neon EVM, you will need to do that already within Solana, because you will need to create PDAs for both of those tokens and ATAs for those tokens, and basically you're gonna, yeah, maybe ignore the first step, kind of, and yeah, maybe not actually.
Okay, I see. So it somehow need to, the two step. It's like two separate step. It cannot atomically like being happen, right?
No, I mean, if you first make a transfer from one EVM to another EVM, and then yeah, you want to make a swap, then only the second part will be done.
Yeah, because the use cases I mentioned is like maybe I want to do arbitrage between two chain. Then if the Solana transaction revert, then I don't want to do this transaction anymore.
Yeah,
so then
yeah.
I have to revert my EVM EVM transaction as well. So
Exactly.
then yeah.
Yeah, so that's a different use case, right?
Thanks.
Thank you.
Do you have any other question? Thank you very much.